This is the third lecture from Chapter 16, and this lecture will discuss how to calculate the pH if you have a weak acid or a weak base. Calculating the pH of a strong acid or strong base is quite simple because you can make the assumption that all of the original acid you dump into a solution gets converted to the hydronium ion. So it's very easy to know what the concentration of hydronium ion is and therefore what the pH is. If you have a weak acid or a base, however, you can't make that assumption. If you drop a weak acid or a weak base into water, of course you're going to get some hydronium ion, but you don't know how much. Okay? You have an equilibrium only if it's a weak acid or a weak base. So some of that acid is going to remain intact, some of it will be the hydronium ion, and of course we need to know exactly what the hydronium ion concentration is in order to calculate pH. Alrighty. So let me give you a couple of specific examples to help you understand how to treat these two problems differently. So let's say that you have a strong acid or a strong base, so it's imperative that you memorize those. For example, here's a typical problem. What is the pH of a 0.050 molar HCl solution? Now, assuming that you're aware that HCl is a strong acid, you can also make the assumption that the concentration of hydronium ion is the same as the original concentration of the acid, in other words, 0.050 molar. My dog is serenading us in the background. And so it's very simple to calculate pH. It's minus log of 0.050, in other words, 1.30. Likewise for a strong base. If you remember, the strong bases are the hydroxides either from with a group 1A metal or the heavy group 2 metal hydroxide. So barium is down at the bottom of group 2A, and so barium hydroxide is a strong base. So since it's strong, that means that once you dump it into water, 100% of that strong base is going to dissociate into the cation and anion, and you're going to have none of the original intact base left. Now, if you're dealing with a base, acid or base, you're going to have to be careful of a couple things. One is stoichiometry, okay? So make sure that you write out this ionization or dissociation reaction before you start doing any calculations. And in this case, you get 2 hydroxides for every 1 barium hydroxide that you dissolve. So the concentration of hydroxide is going to be 2 times the original concentration of the barium hydroxide. In other words, 2 times 0.035. So once you have the concentration, the second thing you have to be careful of is if you're dealing with a base, the concentration you're going to get initially is going to be the concentration of hydroxide. You need the concentration of hydronium, okay, in order to get pH. So you've got to do that conversion that we learned about, I think, in the first lecture. So here's one way to do that conversion. There are a couple ways. So you can find the POH minus log of the concentration of OH. And then if you remember the conversion, pH plus POH added together must equal 14. So we can find pH by simply taking 14 minus the POH, and that gives us the pH. Use your common sense, too. This is a basic solution. We added a base, therefore we expect pH to be greater than 7, and it is. So now that we've reviewed how to find the pH from a strong acid base, let's dig into the more complicated and what this lecture is about, finding the pH of a weak acid or weak base. So the first thing to remember is that a weak acid or weak base, which most acids and bases are, you have an equilibrium and you have some hydronium that's been formed, but also some intact acid. which means anytime you have an equilibrium, you've got to set up an ice table. Okay, and a quick refresher for ice tables. Make sure that you know how to draw out the chemical equation that represents the reaction of an acid in water or a base in water. Remember that pure liquids and solids are left out of the equilibrium expression, so we won't be seeing water in these expressions for Ka and Kb. And then, of course, how to set up your ice table. Remember, unless you're told otherwise, concentration of the products initially is 0. Use X, and remember, when you're filling in your X values, they have to correspond to the coefficients in your balanced equation. In this case, all the coefficients are 1, so they're all going to be X here. Remember your plus and minus signs also. So if you were to have a weak base instead of a weak acid, and for some reason, teachers, textbooks, everything tend to focus on the acids, and you don't get much practice with bases. So if you get a problem with a base, it can easily throw you off. So make sure that you practice the base problems also. They are different. Notice when you have a base and you put it in water, okay, your products are different, of course, than they would have been if you had an acid. And so your Kb expression is definitely going to look different than your Ka expression did. Let's work a straightforward problem. The pH of a 0.1 molar solution of formic acid. Now this is where you have to have your strong acids and bases memorized. And if it's not one of the strong ones, which formic acid is not, that means it's a weak acid, and immediately that means you need an ice table. Okay, so you should kind of train yourself. If it's a weak acid or base, make a note to yourself that you need to draw an ice table. You always want to start out these problems by writing the balanced chemical equation, in this case for an acid, so hydronium is always going to be one of the products, and then the leftover anion, conjugate base. Write then the expression for Ka. I can't emphasize enough the importance of writing out this expression for Ka before you plug in values. On the last exam, a lot of people did a beautiful ice table and then did not show the generic expression for K and just started plugging in the values, and because of that, messed up exponents, coefficients. So please make yourself do both of these. They're also both worth partial credit. All right, so now let's go ahead and work on our ice table. What is the information we have so far? We have the initial concentration of the intact acid they gave us, 0.10 molar. We're going to assume the initial concentration of the products are 0. And then they gave us pH. Okay, so listen really carefully. This is key to solving these problems. pH will give you the equilibrium concentration of hydronium ion. They give you the pH. You can very easily calculate hydronium ion concentration at equilibrium. So do you remember how to go from pH to concentration of hydronium ion? Here's the equation. It's 10 raised to the minus pH. That will give you hydronium ion. They gave us that the pH is 2.38. So 10 raised to the minus 2.38 is 4.2 times 10 to the minus 3. That is the equilibrium. Okay, they're measuring pH and it's assumed it's already reached equilibrium. So that is the equilibrium concentration of hydronium ion and goes here. Now you have two values. You have the initial and the equilibrium value for one of the components, so you can now calculate the change for that component. Once you have the change of any of the reactants and products, you can figure out the change of the rest of them. Look back at your balanced reaction. Look at the coefficients. They're 1 to 1 to 1. They all have assumed 1 in front of them. And so the change for each of them is the same, 4.2 times 10 to the minus 3. Just remember your signs. Reactants are decreasing in general. Products are increasing in general. Then do your math. Okay, in this case, it's a subtraction. In the case of the products, it's addition. Once you have these equilibrium concentrations, go ahead and plug into your expression for Ka. And here we go. The Ka for this formic acid, weak acid, is 1.8 times 10 to the minus 4. Another important formula you will need, and you should probably start listing formulas someplace. There are quite a few of them between pH, pOH, concentration of hydroxide, concentration of hydronium, percent ionization, etc. You have quite a few formulas. So the formula for percent ionization is the concentration of acid at equilibrium, okay, concentration of ion that's formed, over the initial concentration of the intact acid times 100. In the case of percent ionization for a base, okay, obviously the ion we're talking about if we have a base is the hydroxide ion. So that would go in the numerator, concentration of hydroxide at equilibrium, of course, because there's 0 typically initially, over the concentration of the original base, okay, I'm going to put 0 to mean original, times 100. So here's an example. Let's say, as in that last problem, we started with an initial intact concentration of the weak acid of 0.10 molar. That always goes in the denominator. The concentration of ion, which is hydronium ion for an acid, at equilibrium goes in the numerator. Don't forget to multiply by 100. And the percent ionization is 4.2%. For weak acids and bases, this percent ionization is typically quite small. 3.7. As with all of these problems, you can do the calculation either direction. So we used concentrations that we found on an ice table to calculate percent ionization, but you can also use the percent ionization values to determine the equilibrium constant. So for example, if you have hydrofluoric acid, which is a weak acid, and by the way, HF is the only halide-based acid that is weak. So hydrochloric acid, hydrobromic acid, hydroiodic acid, all of those are strong acids. So just thought I'd point that out so it doesn't confuse you later. So in this problem, they're telling you that hydrofluoric acid has a percent ionization in water, 3.7%, and they're asking you to calculate K. So let's talk about what K is first, what we're trying to do. So write out the formula for percent ionization, and then let's go ahead and write out the formula for Ka. So Ka, of course, keeping hydrofluoric in mind, would be concentration of hydronium ion, which I'm just going to shorten H+, times the concentration of the fluoride ion over concentration of HF. Of course, since it's K, all the concentrations have to be at equilibrium. So now the question is, how do we get from percent ionization to this expression for K? Well, believe it or not, the percent ionization actually tells you. What does 3.7% mean? It means that out of every 100 molecules we have of HF, 3.7% of those are going, 3.7 of those are going to be the concentration hydronium ion. So in order to get a percent of something, hopefully you remember from math, you multiply the percentage times the value. So we can easily find the concentration hydronium ion from that percentage. Now, what is the equilibrium concentration of the intact acid? We know the original concentration is 0.250, but what is the equilibrium concentration? Well, if 3.7% of the original intact acid was ionized, that means that 96.3%, that's 100 minus 3.7 is 96.3%. So 96.3% times the original concentration hydrofluoric acid gives you an equilibrium concentration hydrofluoric acid of 0.0241. So the bottom line is you're going to use your percentages to determine equilibrium concentrations. So let's look at what we get on the next page. Once we have all the equilibrium concentrations, we can go ahead and set up our expression for K. Remember that that would be concentration of hydronium ion, concentration of fluoride ion, over concentration of hydrofluoric acid at equilibrium. So we just calculated that concentration of hydronium ion is 0.0092, and from stoichiometry you can see that for every one hydronium that's formed, there's also one fluoride form. So the numerator is actually 0.0092 times 0.0092. We also calculated the equilibrium concentration hydrofluoric acid is 0.241, and that gives us a Ka value of 0.00035. Just with our other ice table problems in Chapter 15, there are also different types of ice problems in the acid-base chapter. One, which we just saw, was to solve for the equilibrium concentration of hydronium ion. This problem is asking you to calculate the Ka for an acid, and yes, this is hypochlorous acid. It is an acid that you should commit to memory because a lot of students make the mistake of looking at it, seeing an OH, and thinking it's a base, but it's actually not. It does this in water. So when you add that to water, this is actually an acidic hydrogen, believe it or not. So here's the conjugate base, and then you get a hydronium ion. Anyway, so this is asking you to calculate a Ka. And so it's an ice table as usual, so I would suggest turning off the video, giving it a shot, see how you can do on your own, and then I'll discuss the answer in the next slide. There are a few things you should get in the habit of doing because they're a good way to show your work for any ice table problem, and they will also get you partial credit. And the first is to write a balanced reaction for what's going on. So in this case, it would be what I already showed you. You could either write out the H2O, in which case you would have to show it as hydronium ion and the conjugate base. Or if you wanted to leave out the water and then just show the H plus instead of H3O, that's fine too. And then you want to always write the equilibrium expression for Ka. And quite a few of you did not do that on the last test, and I have to say the majority of you who did not write the generic expression for Ka ended up making a silly mistake. So here we go. So the Ka expression based on the balanced reaction. I apologize if you hear dog breathing in the background. They're all three following me. Okay, concentration of hydronium ion, concentration of the conjugate base over concentration of the acid, intact acid, all at equilibrium, of course. Once you do those two things, then I would recommend, then and only then, setting up your ice table. All right, so here's the skeleton for the ice table. Remember, liquid water is not part of the equilibrium, so I usually just put a big X under it. The initial concentration of hypochlorous acid is 0.50, and as always, assume the initial concentration of the products are 0 unless you were told otherwise. The other piece of information given in this problem is the pH. That is an equilibrium situation, and the whole purpose of knowing pH is you can use it to calculate hydrogen ion or hydronium ion concentration. So here's the formula. 10 raised to the minus pH, so 10 raised to the minus 3.91 will give you the hydronium ion concentration at equilibrium. And if you punch that into your calculator, you will get that the concentration of hydronium ion is 1.23 times 10 to the minus 4. I love that, 1, 2, 3, 4. So that is your equilibrium concentration of hydronium ion, which means the change for hydronium ion is plus 1.23 times 10 to the minus 4. Okay, since for every one hydronium form, there's one conjugate base form, that change is also 1.23 times 10 to the minus 4. And the change for the original intact hypochlorous acid is minus, I'm going to write this in long form now so it's easier to subtract, 0.00123. Boy, this is definitely a case where we probably could have neglected X. That's going to be really small. Let's see what it is. So then the equilibrium concentration of hypochlorous acid is almost identical. So now we're going to go back to the equilibrium expression. We're going to punch in these equilibrium values, and we're going to calculate K. Alrighty, so here is the generic expression for Ka that we wrote earlier. Here's plugging our equilibrium values in. Do not forget to square the numerator. And if you plug all that in, you should get a Ka value of 2.9 times 10 to the minus 8. And here's yet another problem. Hopefully you're getting my message that the way to be successful in this chapter is to work a ton of ice table problems. So try this one on your own again, and let's see how you can do. Hopefully you're getting yourself into the habit of doing what I told you to do stepwise, and that is write out an equilibrium expression. You need to be able to do that anyway for acid and base. That will definitely show up as a question. This happens to be acetic acid. And so if you were to write the acid ionization equilibrium, it would look like this. So here's the equilibrium constant expression. Setting up your ice table, the given information is 0.3 molar acetic acid and is your initial concentration, 0 for both products. The nice thing about most of these acid and base reactions is almost always, unless it's like a diprotic or triprotic acid, for the acids anyway, there's usually a 1-to-1-to-1 stoichiometry, so you don't have to worry as much about 2x, etc. Now, that won't always be the case with bases, but probably the majority of the time it is. So, using x's, we get our equilibrium concentrations. Remember when it's okay to neglect x. So that's when K is quite small, which it is here, and we're kind of using the rule of thumb of 10 to the minus 4 or smaller exponent, more negative exponent. And since it is, we're going to go ahead and neglect this x. And then plug back into the equilibrium expression. This is what we get when we do so. And go ahead and work that out. Notice we've neglected x here. Okay, we've left that out. And solve for x then, and x represents both the concentration of hydronium ion and the concentration of the conjugate base. Okay, 2.3 times 10 to the minus 3 molar. All right, here's another one. All right, so I'm just going to do the same thing that I always do. I'm going to start out by writing a balanced equilibrium for the acid ionization. And then I'm going to write the equilibrium expression. Okay, so Ka, of course, concentration of hydronium ion times concentration of the conjugate base over concentration of the original intact acid, all at equilibrium. This time they gave us Ka and the initial concentration of the acid. Let's go ahead and set up an ice table. And this time I'm going to put H plus instead of H3O plus because I'm getting lazy. The initial concentration of HCN is 0.025, 0 for the products, minus x plus x plus x, 0.025 minus x, these are each x. Look at that Ka, beautiful. So we can neglect x, so we're going to plug back into the expression for Ka, x squared on top. 0.025, we're going to go ahead and say it's safe to neglect that x because K is so small. And when you solve for the concentration, or for x, which represents the concentration of hydronium ion and the concentration of the conjugate base, well, of course, we're going to get x squared first. X squared equals 1.8 times 10 to the minus 11. So take the square root of both sides, and that tells us that x equals 4.2 times 10 to the minus 6. Remember now that represents the concentration of hydronium ion, so in order to get pH, which is what the question is asking you, you need to take minus log of that concentration, 4.2 times 10 to the minus 6. And when you do that, you finally get your answer. pH is 5.37. Alrighty, you getting tired of working problems yet? I know that I am, but you should work enough problems until they seem silly easy to you, and that's a lot of problems. So, do you remember what percent ionization is? Okay, so percent ionization is concentration of the hydronium ion, if you're talking about an acid, at equilibrium over concentration of the original acid, we're talking about hypochlorous acid here, in its initial concentration times 100. Now, since this problem is asking for the fraction, not the percent, we're going to go ahead and leave off the times 100. And so we already know the initial concentration of the acid. The problem gave it to us. It's 0.500 molar. And that's one of my dogs grumbling in the background. And we need to find the concentration of hydronium ion at equilibrium, which in this case will be Y. So ice table, of course. Original concentration, 0 for the products. There's a 1-to-1 stoichiometry. Can we neglect X? Well, take a look at K. It's very small, so yes, we can. And now we're going to plug these equilibrium values back into the expression for Ka, and they gave us what Ka equals. We're going to solve for Y, which equals concentration of hydronium ion, and then we're going to plug it back in and calculate this fraction ionized. Here's the expression for Ka. They gave us the value for Ka. We take the equilibrium values from the ice table. We neglect Y because Ka is very small. And then we solve for Y, which is the concentration of hydronium ion. Plug that back into the formula for percent ionization. And we get that is 2.8 times 10 to the minus 4th percent ionized. That is an extremely weak acid. It's almost not ionized at all. Now, hopefully, if you've been paying attention at all, you may read this problem and go, wait a minute, isn't that the problem we just worked on? Well, the difference is, and what you're going to get out of this is actually an important realization that is often a multiple choice question. So, and hopefully this will help you remember it. The last problem had 0.500 molar HOCl. And so now there's an even more dilute by a factor of 10 concentration of the original acid. Is that going to affect the percent ionization? Let's see. Go ahead and work it out and see what you get. Alrighty. So I'm going to zip through it faster. We can neglect X. We've already established that with this Ka value that's so small. And so I'm going to go ahead and open up another page and plug into the Ka expression and solve for X. Alrighty, so we're going to go ahead and neglect X again. Multiplying through both sides by 0.05, we get 2 times 10 to the minus 7 equals X squared, and taking the square root of both sides. All right. So the hydronium ion is concentration, or X, is 4.5 times 10 to the minus, I don't know why I have 14 there. That should be 4. And so now remember what we're solving for, though. We're solving for the percent ionization. Oops. Which is the concentration of hydronium ion over the original concentration of the acid times 100. All right, so we just found out the concentration of hydronium ion is 4.5 times 10 to the minus 4. And the original concentration of the hypochlorous acid, whoops, and then times 100. And that gives us, I'm going to write this out long form, 0.89% ionization. What was the percent ionization when we had 0.5 molar, the problem before? It was 2.8 times 10 to the minus 4, or if I write that in long form, 0.00028%. So there's a lot higher, well, they're both really low ionization, but there's higher percent ionization with a lower concentration to begin with. So think about that. An acid is more likely to ionize here. Let me pull up a new page. All right, so this maybe allow you to see it a little bit better. So let's write a conclusion. Okay, as we lower the original concentration of a weak acid. So as we go from here to here, percent ionization increases. So I want you to think about why that might be. I would not require that on my test, but I think it might be a good bonus. And to give you a hint, if you think about the equation for percent ionization, so it's concentration of hydronium ion in the case of an acid over the original concentration of the intact acid. And this ratio, as we dilute it, this ratio is increasing. So see if you can figure out why that might be happening. And I think that'll be one of your bonus options on your next test. Now, as tired as you may be of ice table problems, I want to do one that involves a weak base. And it's harder to find these weak base problems. There aren't as many of them, but it's important because they are really quite different. The most important thing is to get the balanced chemical equation correct for a base. Okay? Remember that a base abstracts a hydrogen atom from water, okay, to give you hydroxide. So the expression for Kb has hydroxide in the numerator rather than hydronium ion. Be very careful when you're working with bases because sometimes a problem will deliberately try to trick you. It'll give you a base and then it'll give you Ka, and if you don't notice that, you're going to get the wrong answer. So remember how to get Kb. Let's say they gave you Ka and you need Kb. You can always find one from the other by dividing Kw divided by the other one. All right, so here we go. Methylamine, any amine, and that means the neutral nitrogen-containing compounds, is a weak base. This problem was nice and gave you the Kb value. So we set up our ice table, ignore water. Initial value, the stoichiometry is all 1 to 1 to 1. And it's probably fine to neglect Y, but we're getting kind of on the border here. All right, plugging our values in and solving for Y. Okay. Now remember that when you solve for X or Y, whatever, what you're getting is the hydroxide concentration. So this problem asked for pH, not POH. So when you take the minus log of the hydroxide concentration, what you're going to get is POH. You then have to convert that to pH by subtracting that value from 14. So our pH value is 11.90, which we would expect because we are dealing with a base, so your pH better be greater than 7. We're almost done. Here's one for you to try, and go ahead and give this a try on your own. This is especially important for you to try. Write out the balanced equation for this weak base. Okay. Write out your Kb expression and set up your ice table. And again, you're calculating pH. Give it a shot, and then I'll go through the answer in the next slide. Alrighty, here is the reaction of this weak base with water. Remember what a base does. It abstracts a hydrogen ion, and that extra hydrogen ion goes on the nitrogen. And hydroxide is always one of the products. It is Kb now that you're setting up. So it is the conjugate acid of the original base times hydroxide all over the original weak base that you started with. So our original concentration of the weak base is 0.35 molar. Hopefully you're getting bored doing ice tables now. Now, can we neglect this X value? What was the value for KB? We sure can neglect it. Very small KB. So that goes out, and now we'll plug these equilibrium values back into the expression for KB. So we have 1.1 times 10 to the minus 8 equals 8x squared over 0.35. We get that x squared is 3.85 times 10 to the minus 9. And x then is 6.2 times 10 to the minus 5. That is the concentration of hydroxide. And so we have to find POH first. Remember, POH is minus log of the concentration of hydroxide, which is 6.2 times 10 to the minus 5. And so POH is 4.21. So then pH, of course, would be 14 minus POH, 4.21. And here we go with our answer, pH of 9.71, which is greater than 7, as a weak base should be. That is it for this lecture on ice tables. Please practice problems.